In this video, we are going to show the image of why we need a common mode feedback CMFB circuits in a fully differential amplifier. Before knowing why we need a CMFB, let's go through why we need a fully differential amplifier. As we know in the wide differential signaling video, the differential system provides better immunity to external common mode interference or noise. With a fully differential amplifier, the matching at the outputs will be better for improving the immunity of a common mode interference. In addition, the fully differential amplifiers would improve the circuit linearity by reducing its even order harmonics. With a good linearity, we could even make sure fully differential amplifiers would truly have twice the dynamic range compared to the single-ended amplifiers. Of course, the twice swing comes from a double circuitry and power of a single-ended amplifier. What kinds of fully differential amplifiers could we have? Think about the low images for 5 seconds. Right, they are passive or active low fully differential amplifiers. For example, we translate the amplifier from input voltage to output current through a transconductance GM. Then, output current will translate back to voltage through the impedance of the load, which is VL equals IL times RL. So, the voltage gain of the amplifier will be VL divided by Vin. And the output load is very important to set the output voltage or the output bandwidth, which can be a passive resistor or active transistor shown here. Then, let's check their output common mode voltages respectively. For the passive low differential amplifier, the output common mode is simple. As you can see, the current is only set by the tail current source Is. So, the output common mode voltage would be VDD minus half Is times RD, which should be stable, since both Is and RD will be stable. Therefore, the output common mode level will be well defined with no issue. How about the output common mode of the active amplifier? For the active low differential amplifier, the output common mode will be set by the top current source IP and the tail current source IN. Therefore, the output common mode voltage will vary, since it's hard to match the source current IP and the sink current IN at the bottom. If the IP is greater than IN from the DC biasing, the KCL loop will balance the current IP the same as the IN by increasing the output common mode voltage. Do you know why? Think about the transistor's DC IV images for 5 seconds. Bingo! As you can see, ideally, the current will be constant in the saturation region, and the only way of varying or decreasing the current is to reduce the VDS and push the transistor to the trial region. What's happening of the IP current negative feedback loop is that the output common mode voltage will shift up, and then the VDS of the M34 will be decreased and push the M34 into the trial region. So, the IP will be decreased to be equal to the IN, even though both the biasing voltage VP and VN stay the same. Similarly, if the IN is greater than the IP, the tail transistor will be pushed to the trial region, and then its IN will be equal to IP. If the output common mode is not well defined. What could be the issue? Think about the amplifier operation images for 5 seconds. Correct. The first issue is the output common mode drift will cause any transistor inside the amplifier to the trial region. In the beginning, we want the active load instead of the passive load to increase the output impedance, Rout, and the voltage gain. Obviously, the Rout of the M34 will be reduced a lot from the saturation region to the trial region. Therefore, we could dismiss the original design goal. Second, we may need to cascade this amplifier stage to a following circuitry or amplifier stage, even though the output common mode drift will not degrade the performance of this amplifier. It may push the following stage circuitry into trial region and degrade the whole system's performance. Third, both advantage of the linearity and the twice dynamic range compared to the single-ended amplifier will not hold anymore. For example, the output signals could be clipped if the output voltage mode drift up or down too much to destroy the linearity. In order to maintain the linearity, the output swing or dynamic range must be constrained as well. After understanding the images of the common mode drift issue, how do we fix it? Think about your correction images for 5 seconds. Bingo! Just add a negative feedback loop to correct with a reference voltage level. As you can see, we could simply sense the output common mode and then compare it to a reference VREF by a comparator, which could be an output transconductance amplifier, OTA. If the VCM is greater than the VREF, the output voltage of the OTA will be higher to increase the tail current IN, and the output common mode voltage VCM will drop to the VREF. On the other hand, if the VCM is smaller than the VREF, the output voltage of the OTA will be decreased to reduce the tail current IN, and the output common mode voltage VCM will increase and the same as the VREF. So, the output common mode voltage will be the same as the VREF for sure. But how do we sense the output common mode from the differential nodes? Think about the common mode images for 5 seconds. Right, the voltages at the differential output nodes include both differential and common mode signal. If we add or show both outputs together, the differential signals will be gone, and only the common mode signal is left. Can we really show them? Of course not. Remember, the differential signals will be gone. So, we may need to isolate the differential signals with a high impedance of the common mode sensing. The simplest one is to add a large resistor here. If the sensing resistor Rsense is greater than the amplifier's output impedance by more than 2 orders of magnitude, the Rout of the amplifier will be almost the same, and the amplifier's gain is maintained without being loaded by the common mode sensing. On the other hand, the output common mode voltage is extracted by taking the center tap of those 2 resistors easy. Here are the summarized images of why we need a common mode feedback CMFB circuits in fully differential active low amplifiers. Since the output common mode voltage is not well defined due to the current mismatch between the source current IP and the sink current IN, at the bottom, A common mode feedback, CMFB, is needed to keep the common mode voltage well defined. A simple common mode sensing by two big resistors can extract output common mode level without loading the differential mode operation. So, by making the output common mode voltage VCM well defined as the VREF, will make all the transistors in a fully differential active low amplifier stay in the saturation region easily. In addition, the stable VCM will simplify the following stages input common mode in design to make the whole system robust in voltage gain, linearity, and output dynamic range. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.